Imagine a world where every single request to a database, no matter how frequent or simple, had to hit the primary storage. The latency would be crippling, and the load on our backend systems would be astronomical. That's where caching comes in, a fundamental technique to boost performance and reduce load. But while caching seems straightforward, it's also a minefield of potential pitfalls. Did you know that a poorly implemented cache can actually increase latency and system instability rather than decrease it? It's a common trap many developers fall into, often leading to subtle, hard-to-debug issues that only manifest under specific load conditions. In this deep dive, we'll peel back the layers on common caching mistakes, explore why they happen, and arm you with the knowledge to build more resilient and performant systems. We'll start with the basics, move into complex invalidation problems, analyze real-world failure patterns like the thundering herd, and finally look at advanced mitigation strategies and future trends. By the end, you'll have a much clearer understanding of not just how to use a cache, but how not to make it your system's Achilles heel. Before we delve into what goes wrong, let's quickly re-establish the core purpose of a cache. At its heart, a cache is simply a high-speed data storage layer that stores a subset of data, typically transient, so that future requests for that data can be served up faster than accessing the data's primary source. Think of it like your brain's short-term memory. Frequently accessed information is kept readily available for quick recall, while less used or older memories require more effort to retrieve. This principle is vital because primary data stores like databases or remote APIs are often slow, expensive to query, or have rate limits. Caching reduces latency by bringing data closer to the application or user, and it significantly offloads the backend, allowing it to handle more requests or perform more complex operations without being overwhelmed by repetitive data fetches. Understanding this fundamental trade-off between speed and consistency is key, as many caching mistakes stem from mismanaging this balance. We're essentially trading a potential for stale data for a massive gain in speed and efficiency. The challenge, then, is to manage this trade-off intelligently. One of the most insidious problems in caching is cache invalidation. This isn't just a theoretical problem, it's a practical nightmare that can lead to users seeing outdated information, or worse, making decisions based on incorrect data. The core challenge lies in ensuring that the data in the cache remains consistent with the primary data source. When the primary data changes, the cached version must be updated or removed. Common mistakes here include relying solely on time to live, or TTL, which is a fixed expiration. While simple, if the underlying data changes before the TTL expires, your cache now holds stale data. Another pitfall is inadequate explicit invalidation. If multiple services write to the same data source and only one service knows to invalidate the cache, others might continue serving old data. Distributed systems compound this, as invalidation messages might be delayed or lost. This can lead to what's known as eventual consistency that's more eventual than consistent in practice, leaving users frustrated. The lack of a robust invalidation strategy often leads to a false sense of security, where developers assume data is fresh, only to discover critical discrepancies in production. This is where a clear understanding of your data's consistency requirements becomes paramount. Let's look at a classic caching failure pattern known as the thundering herd, or cache stampede. Imagine a scenario where a highly popular news article or perhaps a sudden spike in product availability causes thousands, even millions of users to simultaneously request the exact same piece of data. If this data isn't in the cache, or if its TTL just expired, all those requests will bypass the cache and hit the primary data source concurrently. This thundering herd of requests can overwhelm your database or API, leading to slow responses, timeouts, and potentially a complete system outage. It's a self-inflicted denial of service attack. A common mistake is not implementing proper request coalescing or a single flight mechanism where only one request is allowed to fetch the missing data from the backend, and all subsequent identical requests wait for that single fetch to complete before being served from the newly populated cache. Without this, even a momentary cache miss on a popular item can cascade into a full-blown system collapse during peak load. We often see this during major sporting events, flash sales, or breaking news, where an expected surge in traffic finds an unprepared caching layer, turning a minor cache miss into a catastrophic event.
So how do we prevent these common caching pitfalls? It starts with a multi-layered approach. Implement robust invalidation strategies, perhaps using event-driven invalidation or write-through caches for critical data. For thundering herd scenarios, crucial techniques like request coalescing, where multiple requests for the same missing cache item are grouped into a single backend fetch, are indispensable. Consider circuit breakers and graceful degradation. If your cache or backend is struggling, fail fast and serve slightly older data or even a stale while revalidate approach rather than crashing the whole system. Prefetching popular content before it's requested can significantly reduce cache misses during anticipated spikes. Looking ahead, the future of caching is exciting. We're seeing more intelligent, AI-driven caching systems that learn access patterns and predict what to cache, optimizing hit rates dynamically. Edge caching is becoming more prevalent, pushing data even closer to the user to minimize latency. Serverless architectures are driving new patterns for transient, highly scalable caching. The lesson here is clear. Don't treat caching as an afterthought. It's a critical component of system design, demanding careful planning, continuous monitoring, and an understanding of its inherent complexities. The more you understand its potential failure modes, the more robust your systems will be.